Hey everyone, in this video we are going to talk about section 5.1a, which is about differential equations and antiderivatives. So unit 5 will extend what we learned about integrals in unit 4. Unit 5 is really big to the point where I actually split it into two separate mini units. So unit 5a, as we will call it, we will learn methods of integration, and in unit 5b we're going to develop the idea of differential equations and slope fields, and we're going to apply calculus to real-world scenarios. So this video is going to introduce us to both parts of unit 5, because we can't really talk about integrals if we first haven't talked about differential equations first. So that's what this video is about. It is spliced from a couple of past videos together, so enjoy. Today, though, we're talking about differential equations. So what you need to know about a differential equation is it's basically an equation that is some other unknown equation's derivative. So it's like we're starting with the derivative of some other type of function. So when we're finding solutions to differential equations, it really has to do with finding the antiderivative of that differential equation. So what was the original function that is this function's antiderivative? Okay, so it can have two different types of solutions. We can have general solution, where we know some value of a constant, or we can have an exact solution, but we have to be given an initial value. So looking at example 1, I see here that I have all these different differential equations. So I can tell they're differential equations because I'm given this the dy dx, right? Dy dx really tells us that we have a derivative. Okay, so we're starting with the derivative. Let's go back and find its original function. What's the antiderivative? Here in this case, we're going to find the general solution. Right now, we'll talk about what general means. We're going to focus first on just finding the solution portion. Okay, so let's look at number 1. I should probably write here that our goal is to solve for y of the original function. So we're trying to write it as like y equals function. Okay, cool. So looking at A, we have dy dx equals 5x to the 4th minus secant squared x. Okay, hopefully I've posted another video first before this that you watched that explain what a differential was. In that video, if I didn't, please let me know and I can go back and post it or explain what a differential is. But what we know is that this dy dx, we're going to think about this as a fraction. I know that it's not a fraction, but it behaves like one. So what that means is we can split this up, and I'm going to multiply the dx over to the other side. So I'm going to have dy is equal to 5x to the 4th minus secant squared x times dx. And so once I have that, what I'm going to do is I'm going to integrate both sides. So this integral symbol, we've really thought about that with like having numbers here, right, like a and b, and so that's telling us that we're finding this accumulation of area under the curve. Okay, well, when we don't have the numbers here, this is what we call an indefinite integral, and really that indefinite integral just is telling us that we are going to antiderive. So that's like instructions, like find the antiderivative of this. Okay, so we're finding the antiderivative of dy, and then we're finding the antiderivative of 5x to the 4th minus secant squared of x. Okay, well, so if we have this dy, let's think back to when we were doing kind of like our, well, is that what I was saying? Maybe not. Okay, well, so dy. Okay, maybe this is what I'm trying to say. Let me explain. You know when we were doing like implicit differentiation, when we'd have like x's and y's together, we were talking about relations, and we'd have to find the derivative of something with like respect to x, respect to y. Yeah, so when we were finding the derivative of something with y with respect to x, we always wrote like dy dx after that to say, hey, we are deriving y or x. Okay, well, since I have dy, the integral of that is really just going to be y. So the indefinite integral, the antiderivative of dy is y. Okay. Well, now let's go back and let's find the antiderivative of each of these parts. Well, 5x to the 4th, that's like a power rule, right? We have to do that backwards. So I'm going to add 1 to the exponent, so that becomes 5, and then I'm going to divide by that exponent. Okay, we'll clean that up in just a second. And then I have this secant squared x. Well, okay, that's like a trig. What function gives you a derivative of secant squared x? That's tangent. It's minus tangent of x. Okay, and then cleaning all of this up, it's going to be x to the 5th minus tangent of x. Okay, so here is one type of antiderivative. Here's one solution. I could also have a solution that maybe looks like this. Maybe I have y equals x to the 5th minus tangent x plus 8. That's another solution, right? Or I could have y equals x to the 5th minus tangent of x plus 10,000. That's another solution. So really what you're seeing is I am adding some sort of constant onto the end. And I could keep adding constants. Maybe we wanted to do negative 11.5 or pi or anything like that, any sort of constants. So thankfully, when we're finding the general solution, I don't need to list out all of the possible infinite number of constants that I could have at the end. What I'm going to add on is I'm going to add a plus c. So that c is really standing for some sort of unknown constant. We maybe have talked about this before, but that's just saying, hey, I'm recognizing that there might have been a constant, the derivative of that constant would have been 0, so that possibly could have been there. Okay, so that was number, well, A. Let's look at B. Okay, so we have this derivative, dy dx is equal to negative 1 over the absolute value of x times the square root of x squared minus 1 minus 1 over x. So I'm already going to go ahead, I'm going to separate out my differentials. So I'm going to have dy is equal to negative 1, all of this good stuff. And all of this is being multiplied by dx. Okay, so since we're trying to find the solution, we're going to integrate both sides. Okay, integral of dy is just going to be y. And now we need to find the antiderivative of each of this. Okay, well, this thing over here is pretty crazy, so that tells me it's probably going to be some sort of inverse trig function. And as it turns out, that is inverse of cosecant of x. Okay, and then, okay, what function's derivative is 1 over x? Aha, well, that's going to be natural log. Okay. And since we're finding the general solution, I want to make sure I'm adding on that plus c. Well, one thing that we've talked briefly about before, but I'm going to bring it up again, is that the domain of a solution has to match the domain of a differential equation. So let me write that down and I'll explain what that means. Okay, so what that means is if I were to find the domain of 1 over x, well, I know that that domain is like negative infinity to 0 and 0 to infinity because we have that vertical asymptote. Okay, well, right now our domain of the solution, natural log of x, ooh, well, that's just 0 to infinity, right? Because we can't have negatives, can't actually include 0. So we need to do something to natural log, so I include this part, all of the negative numbers. And I think we've talked about this a little bit before, but our fix for that is we're going to put the x in absolute values. So right now how I have it written out, this is technically not correct. How we want to write this is y equals cosecant inverse of x minus the natural log. I'm going to put that x in absolute values. And that's because when I put in negatives, okay, that's in the domain, I can put in positives, that's in the domain, still can't put in 0, but that's okay because that matches the domain. So now, adding this portion, I end up getting this part of the domain. I think we talked about that before, but just in case we didn't. All right. And let's look at our last one. So one thing you'll notice that we've added a plus c on each one of these. On every AP style question, you're going to stop earning points when you forget to write plus c. yeah, that seems harsh, right? So a lot of the times you're going to find some sort of antiderivative or some sort of solution to the differential equation, and then you're going to do something where you have to evaluate it. Well, if you don't have that plus c, basically your work after that is invalid. You have to have that plus c because that constant that you're going to have is going to affect what your other solutions are. So that plus c is worth a point, but it kind of determines what other points you get after that. So always remember to add plus c. So with that in mind, let's look at c. So I'm already gonna split this up. Oh, went too far. There we go. Okay, so we'll have dy equals 7x to the 6th times secant squared of x to the 7th, and we multiplied over that dx. Okay, so we're gonna antiderive both sides. Okay, so we've done a lot where we're adding or subtracting some different functions together, but we haven't had anything where we are multiplying those functions together. So this is where we're going to have to start looking for some little hints. So if I focus here just on this secant portion, well, I know the antiderivative of secant is tangent, right? Okay, so if I have this tangent, what's inside of it? Okay, well, that's kind of like an x to the 7th. So right now, if this was my function, if I were to antiderive it, this becomes a chain rule. So the derivative of tangent would be secant squared of x to the 7th, and then we'd have to multiply it by the derivative of the inside, so 7x to the 6th. And hey, I see that matches what I have in here. So we have to recognize that this was really just that derivative of the inside of our other function. So this becomes tangent of x to the 7th, and I need to make sure I add that plus c. And we're going to have a lot of fun trying to figure out how to undo the chain rule. In fact, section 5.2 has a bunch of different parts to it. We're going to spend all of our time trying to figure this out. So this is just a little taste of the fun that we're going to have soon. Okay, one other thing that I'm going to address before we move on. So you might be wondering, okay, well, if we're antideriving both sides, do we need to put a plus c on both? Yes, but also no. So what that means is, if I were to antiderive the dy, well, technically that's y plus some sort of constant. Let's call that c1. Okay, antiderivative of all of this, that's tangent times x to the 7th plus c2. Okay, so if I were to move all of my constants over really to solve y, subtracting c1 on both sides, well, isn't just a constant minus another constant just some other type of constant? Yeah, it is. So that just becomes c. Right? It's some other constant. So we're recognizing that really we do have constant on both sides, but it ends up being this when we solve for y at the very end. Hopefully that makes sense. If not, we can talk more about that when you're in person. Okay, let's flip over. So we spent a lot of time finding the general solutions. Now we're going to find the particular solutions. And so if we're going to find the particular solution, we're going to talk about this as an initial value problem. So we're going to be given some sort of information, and our whole goal is going to be to solve for that c. So before we were just saying, hey, there's some sort of constant, let's just move on. Here we're going to be given some information we can actually plug in to find c. So good news is it's what we've been doing before. Bad news is we have to do just a little bit more work. But good news is this is kind of more practice of what we were just doing. Okay, so looking at example A and 2, okay, I'm going to already split this up. So we're going to have dy is equal to negative 1 over t squared minus 3t to the 4th plus 12 times dx. Okay, and right now I see that I have some variables in the denominator. I'm going to rewrite this just a little bit so I can see their exponents better. So dy is equal to negative 1 times t to the negative 2nd minus 3t to the negative 4th plus 12 dx. Okay, so now I have it this way. Let's antiderive. So give me a y. And now this just becomes a bunch of power rules that we need to undo. So I know that I'm going to add 1 to the exponent, so negative 2 plus 1 is negative 1. Divide by that new exponent, divide by negative 1. Okay, and I know we have a bunch of negatives here. We'll clean it up at the end. Okay, so minus 3t, I'm going to add 1 to the exponent. That will be negative 3. I'm going to divide by negative 3. In this case, I just have a constant 12, so I just need to add a variable to it. So plus t, and I need to add that plus c. Okay, let's clean it up as promised. So negative divided by negative, that's just going to be t to the negative first, negative 3, t to the negative 3. Alright, okay, and then let's just solve a little bit. Oh, my dog is barking. Ignore him. Okay. Oh, getting distracted. Hey, buddy. Buddy, it's okay. Oh my. He's on guard dog duty. Okay, here we go. So this is our general solution of the differential equation. Okay, but we're given some sort of information. We're going to find c when we know that y is equal to 3. Wow, I am so sorry. We're just going to ignore him. Okay. We're going to find this when y is equal to 3 and t is equal to 1. So I'm going to plug in 3 for y and 1 for t. Here we go. Okay, and then solving for c, let's clean this up. 3 equals 1 plus 12 plus c. So let's come over here. That's going to be 14 plus c. So solving for c, we get c equals negative 11. All right, cool. Remember, our goal was to solve for the particular solution, so that means that I need to actually go back and replace this plus c with negative 11. So our official answer would be y equals 1 over t plus 1 over t cubed plus 12t minus 11. All right, there we go. And then, okay, for this last one, why don't you try this on your own? So pause the video, try it yourself, unpause the video, and we'll check our answers. So give you a little time. All right, welcome back. I'm going to write up our answer. We'll check it and see how we did. So our particular solution to this differential equation when a is equal to 0 and r is equal to 1 should be a equals the natural log of the absolute value of r plus 1 over r plus 6r minus 7. So here's our official answer. If you got that, great, good. You're good to stop the video and sign off, and I'll see you later. If that's not quite what you got, let me explain how we got there. So I know from here, I would have split up my variables, so dA is equal to 1 over r minus 1 over r squared plus 6, and all of that would be multiplied by dr. I probably also would have fixed my exponents a little bit, just so I can do those power rules. Okay, and now we can start to antiderive. Boom. So antiderivative of dA is just going to be a. Okay, and so then if we got to here, r to the negative first, if I add 1 to the exponent, well, now I just get r to the 0. I know that's not right, so that would kind of be our clue to the fact that 1 over r's antiderivative is going to be the natural log of r. But remember, we need to put it in absolute value, so natural log absolute value of r. Okay, for this next part, let's add 1 to our exponent, so r to the negative first. We're going to divide by that exponent. I'm going to give that 6 and r, and then we need to add a plus c. Okay, so cleaning this up. Let's see, this is going to be plus, well, this is just going to become 1 over r plus 6r plus c. Okay, now that I have all this information, we can use our initial conditions that we are given. So a is equal to 0, and now all of our r's will be 1. So natural log of 1 plus 1 over 1 plus 6 times 1 plus c. All right, so let's see, 0 equals natural log 1 is 0, plus 1 plus 6 plus c. 0 is equal to 7 plus c. And so that means that c is equal to negative 7. So we would have taken that negative 7, we would have plugged it in for c here. To finish off this video, we are going to switch gears and look at indefinite integrals. We'll write back to differential equations in the latter half of Unit 5, but for now, we'll be focusing on indefinite integrals. So Unit 4 dealt extensively with definite integrals, where we're specifically calculating the area under the curve using things like geometric formulas, definite integral properties, even our F integrate on our calculator. Definite integrals will have bounds on them. Indefinite integrals, on the other hand, do not have bounds. So here I know that this is a definite integral because I have my bounds a and b, but here I can see that this is an indefinite integral because there is no such a, b within the integral symbol. So when we are told to find the indefinite integral, our task will be to find the antiderivative and determine a function. So to clarify, definite integrals will produce areas, while indefinite integrals will produce an equation. And of course we know that because when we find an antiderivative, we are going to have a plus c on the end. So example 3 that we have here is simply what we were doing before in our prior examples. And I don't think we really need to do a whole lot more together. The only difference is we don't need to separate the differentials, and we're already given our integral symbol. So I'll have you go ahead and have you pause the video, try to find the antiderivatives for both a and b, and then we'll check together. All right, welcome back. Have you had a chance to try it out yourself? Here are our answers. So for a, our indefinite integral, our antiderivative should be 1/3 t cubed plus 1 over t plus c. And for b, we should have 3/5 x to the 5th plus 1 over x squared plus tangent x plus c. So I'm not going to go through and show the process for doing it. So if you have questions, make sure that you ask me in class next time you see me. The last example within this section says to use differentiation to verify the antiderivative formula. And so all this is that we can always double check our answer to make sure that we've done the process right. So for a, we have the integral of e to the 2x dx, and we're told that's equal to 1/2 e to the 2x plus c. So if we wanted to check and make sure that this is actually a true statement, we would just need to derive this and make sure that it equals this here. And I'll have you try that out yourself, so on your own. Same thing with b, so here we're given that the integral of 1 over 1 plus u du is equal to tangent inverse of u plus c. Again, we can derive the antiderivative, and it should get us back to what our integrand was. And again, try that out on your own. So that concludes everything that we have for this video, so I will see y'all in class, and see you later.